Finally, here is not about solving congruences, but a bonus theorem about congruences, which is called Fermat's little theorem. And let me just use this. What is the theorem? If P is prime and A is any integer coprime to P, let me say relatively prime, because I haven't used that word before. Or let me even say P does not divide A. So this is the same as saying that they're relatively prime, because the only factor they could have in common is P. Then, so essentially this is also saying that A is not 0 mod P. This is another way of thinking about it. So if this is the case, then A to the power P minus 1 is congruent to 1 mod P. So this is, might not be totally obvious from the start what this theorem is saying or why this theorem is interesting. So let me make a couple of little comments about it. It's nice for a couple of reasons, because it's sort of helpful for working with arithmetic mod P. So first of all, it gives you basically a very easy way of finding an inverse of A mod P. It's just A to the P minus 2, because if you multiply them, you get this. It also, if you're interested in computational aspects, it's a very efficient way of finding high powers of A, because this power is always congruent to 1, so you can just cancel that out and keep canceling that out, and it makes exponentiating things very fast, which is nice. But I want to talk about another application, and I think we'll get to another application tomorrow. But the application that I want to talk about today is probabilistic primality tests. So what is a probabilistic primality test? Remember that we talked about some quite basic primality tests, not yesterday, but maybe 2 days ago, that one of them is to just divide it by a lot of things and see if any of them take, which is trial division. And the other one was the sieve of Eratosthenes, which essentially sieves out a lot of primes using a similar sort of technique. So the problem with these is that they're extremely slow at determining if a number is prime or not. It takes a very, very long time. One thing that you can do is, so an alternative is these probabilistic primality tests, which don't tell you for sure if a number is prime, but they will tell you that a number is quite probably prime, and they will do it much, much faster. So here is one such thing. Converse of Fermat's little theorem if P is an integer such that for any A so let's say any integer less than P that is relatively prime. So if P is an integer such that everything relatively prime to P satisfies A to the P minus 1 is congruent to 1 mod p, then p is prime. So how does this give us a probabilistic primality test? Well, the fact is that this is not true, but counterexamples are rare. So this gives us a way of testing whether a number is likely to be prime by take some number a, raise it to this power, and see if it's congruent to 1. If it is, then your number is probably prime. And if you check a bunch of these a's, you get more and more confident. And the fact is that this statement is not true, so there are integers p that will satisfy this test, but still are not prime. But they're very rare. So, okay, so let me write some of this down. If a to the p minus 1 is concurrent to 1 mod p, then p is likely to be prime. If we check many a's, we get more and more confident. And just to put some actual numbers on this, what do I mean by confident? So for example, up to 10 to the 21, the probability of a number being prime is, how would you find this? A little callback to a couple days ago. You may remember that we have this thing called the prime number theorem that tells us about how many numbers are prime up to a certain bound. And the bound, so little review that I'll erase, they're about 10 to the 21 divided by ln 10 to the 21 primes up to 10 to the 21. So if you pick a random number and ask if it's prime, that's going to be about 1 in 1 over ln 10 to the 21, because that's just dividing this number by this number, or I guess multiplying them. You're dividing something by something. Anyway, this is what the probability is. Let me not be precise about this at all until we talk about probability. Oh, jeez. No. Okay, but you can compute that, whatever. The probability of a number being prime up to this bound is about 1 in 50. So if you choose a random number, 1 in 50, it will be prime. So this is from the prime number theorem. And the probability a number passes this test, but is not prime, is about, so this is something that we haven't talked about how to compute. I mean, you know, you're just counting how many numbers satisfy this strange property, but someone has counted that, and it turns out to be about 1 in 50 trillion. So if you choose a random number and try a lot of possibilities for A, and it checks out in every case, then you start to become quite confident that your number is prime. The chances that you are wrong are going to be about 1 in a trillion. And if you increase this number, so that's a prime with 20 digits, 21 digits. If you think about a prime with 100 or 200 or 300 digits, you get more and more confident. So the chances are going to be even much better than 1 in a trillion that you're wrong. And so this is the basis of, not this specific test, but things very close to this are actually more often how people test for primality.